Hi everyone, my name is Gracie and this is my last presentation for the physics lab. So the purpose of the lab is to observe the difference between a computational and an observed model of a falling slinky and seeing if our computational model matches what actually happens in the video. And the major physics principles used in this is going to be Newton's second law, the gravitational constant, tension, force, and drag. The system is the slinky, particularly the bottom of the slinky, and this mass I got from Googling what would the mass of a slinky of that size be. And the surroundings are gravity, tension, and drag. Those are the forces acting on the slinky. And the initial conditions are that it's being held in the air at rest. So it's uncoiled, meaning that the bottom hangs freely, and so there's not a strong spring force. So the main objective is to compare the elements of movement observed and compare it to the video we saw. And the prediction is that the computational model will mirror the video in that we'll see a motionless state before the top of the slinky meets the bottom, and then they'll fall together. So brief overview of the results. Our prediction was right. As you can see, they sit there at rest because we tracked the bottom of the slinky specifically. So as you can see, it kind of sits there at rest before falling in a linear fashion after this time period, which is when the top of the slinky met the bottom. So this is the video we used. As you can see, the bottom of the slinky is sitting there motionless until the top reaches it, and then they fall together. So we analyzed this in the tracker app. We just used the point mass tracking feature, and frame by frame, we kept track of the position, and we calibrated it to the mass, and I set the coordinates so that the bottom of the slinky would be at the origin. And I used the base of the computational model used in lab 2, where we dropped a light object and observed the drag force. And the changes I made to it include the F-net. So while t is less than 4.2, this is before the top of the slinky meets the bottom, the two forces, we know that the forces acting on the bottom of the slinky are canceling out. So the gravitational force and the tension force are going to be what's holding it in place since we don't see any net movement. And then after the top meets the bottom and they start falling, we can see that F-net is going to change. Now the two forces acting on the slinky are gravity and drag. It's no longer tension. And so this is when you see it falling. So this is the main difference that I made. And once again, the results show a similar graph. This was just taken from the output of the program, and this was taken from Excel. And as you can see, this is the point where the top collides with the bottom and they both start falling together. And this is due to the forces acting on the slinky changing. So possible sources of differences was that there wasn't, the model in Python was not taking into account the small x component change, like a little bit to the left or right. And also, as you can see, this isn't quite linear, and this is because it was done by manually tracking it frame by frame. And a potential error could be calibration issues. We don't know the exact weight of the slinky. I Googled that. So additional questions. Does the bottom of your model slinky stay stationary just like in the video? Yes, the model reflects the forces acting on the bottom of the slinky transitioning from at rest to unbalanced. So once again, these are this is time versus y position. So as you can see, it is motionless, kind of suspended in the air, and then it starts falling. And then, would we observe the same motion if the slinky was longer and held higher in the air? I think yes, we would, and this is due to the fact that it's only when the top of the slinky reaches the point where the bottom is, the tension force holding the bottom of the slinky in place against gravity, this force will be suspended, and then it turns into gravity and drag that makes it fall to the ground. Thank you.